Good morning, students. In our last class, we discussed about the cells EMF and internal resistance. So from that, we get the relation that is V is equals to E minus IR. So where E is the EMF of a cell and V is the potential across the cell and I is the current which is flowing in the external circuit and R is the resistance. So this resistance is the internal resistance, right? So small r is the internal resistance and I is the current flowing and E is the EMF of the cell and V is the potential, right? So from the Ohm's law we have V is equals to IR. So this is the current which is flowing in the external circuit. So when an external resistance, right? So this we taken as the resistance R which is connected across the cell E comma internal resistance R, right? So when an external resistance is connected to the EMF, that is to the cell, so from the Ohm's law we get the potential across this resistance is V is equals to I into R, right? So here V is the potential across the cell. So hence these two potentials are remain same. So we can relate this one as IR is equals to E minus IR, right? So the total current which is flowing in entire circuit, we can find I is equals to E divided by R plus R. So where R is the external resistance which is connected to the cell and where small r is the internal resistance, right? So these two are very important relations. So one is V is equals to E minus IR and another one is I is equals to E divided by R plus R when an external resistance is connected to the cell. So when internal resistance R is equals to 0, the internal resistance of the EMF of a cell is 0. So we get the current. So that current is the maximum current. I maximum is equals to E divided by R. Right? So that is directly we relate V is equals to E because the internal resistance is 0. So we can write V is equals to E. That is again from the Ohm's law we get I max is equals to V divided by R. Right? So this is we discussed in our last class. So here also we can combine across the cells or combination of cells. So very important combination of cells. So this is also similar to that of the combination of resistance and also combination of capacitors. Right. So in that class we will discuss cells connected in series. Right. So very important for 5 marks. Either they ask for cells which are connected in series or connected in parallel. In 2019 they asked for the relation to find the two cells which are connected in parallel. Right. So same as that of the resistance, right? So considering two cells of EMF E1 and internal resistance R1, right? So on the current which is flowing in the cell, that is taken as I, right? So consider one more cell of EMF E2 and internal resistance R2 and the current flowing in that circuit is also I. So E cell kuda current I flow agtide because these two which are connected in series. So connected in series means one end of the cell is connected to the another end of the cell and leaving other two terminals left free, right? So one end of the first cell is connected to the another end of the second cell and leaving the other two terminals free, right? So this combination we call as combination of cells which are connected in series, right? So here also current flowing is I, right? So naming the terminals A, B and C, right? So now we are going to find the combination of the two cells which are in series, right? For that, first to find the potential difference between A and B, right? Potential difference between A and B. That means potential difference across the cell E. So first cell across cell potential ಎಷ್ಟಿದೆ ಅನ್ನೋದನ್ನ find out ಮಾಡ್ತಾ ಇರೋದು. That is from the relation. So ಇದು ನಮಗೆ ನೆನಪಿರಬೇಕು. V is equals to E minus IR, right? So by using this relation where V is the potential difference across the cell. So here we have the 2 points, right? So that one, the potential difference VA minus VB, right? That is equals to EMF of the cell. We taken that one as E1 minus IR1. I is the current which is flowing in the cell, right? So similarly, the potential difference between B and C, the potential difference between B and C. So we write that one as VB minus VC, right? So that is equals to EMF of the cell E2 minus IR2. So E2 is the EMF of the cell, second cell, and R2 is the internal resistance of the second cell. So that we return from the formula V is equals to E minus IR, where E is the EMF of the cell, I is the current which is flowing across the cell, and R is the internal resistance of the cell, right? So now the total potential difference between the points A and B. So idu namme individual cells potential ಕೊಡ್ತಾ ಇದೆ. So we connected the two cells in series. So hence the potential difference between A and C. So that we can write VA minus VC, right? So potential difference across A and C, VA minus VC. So this we can write VA minus VB. That means adding and subtracting the potential VB minus VB plus VB minus VC, right? Or if we add these two, we get VA minus VC, right? So we are going to add model kuda namage barutte, or we can write by adding and subtracting the potential VB, right? So from this VA minus VB we can write in place of VA minus VB, so that is E1 minus IR1, right? So next VB minus VC we can write that one as E2 minus IR1, right? So here we can write this one E1 plus E2 plus, so minus. So in these two terms we can take I common, that is R1 plus R2, right? So minus I we taken common, so we get R1 plus R2. So this gives what? The potential between is, right? So calling this one as first equation. So total potential difference between A and C, we can write this one as sum of two cells EMF minus current into the sum of two internal resistance, right? So now comparing this one with the equivalent EMF as we did in the last class, that is equivalent resistance. In the same way here we have the equivalent cell. That means this cell same work will done in the combination of these two cells. So ಈ ಎರಡು cells ಏನು work ಮಾಡುತ್ತೋ ಆ work ಇದೊಂದೇ cell ಮಾಡುತ್ತೆ. So that's why this we call as equivalent cell. So we call this one as EEQ. That means EMF of the equivalent cell we denoted by EEQ. EQ represents what? The equivalent cell, and the internal resistance are EQ, and the current which is flowing is I, right? So taken this one as AC, right? So from the definition, so we can write V AC, that is equals to E equivalent minus I R equivalent, right? So take on this one as second equation. So this is from definition or from the formula, right? So now comparing these two equations 1 and 2, we have the common voltage across the two cells, right? So VAC and VAC. So if the LHS are equal, we can directly relate the RHS, right? So in place of AC, we can write E EQ minus I into R1 plus R2. I into R EQ, right? So that is equals to summation of E1 plus E2 minus I of R1 plus R2, right? So now if we compare these two, so in place of E equivalent, we are getting E1 plus E2. So in place of R equivalent, we are getting R1 plus R2, right? So from this, we can write E equivalent, that is equal to E1 plus E2, and R equivalent, that is equals to R1 plus R2. So this gives what? The final expressions for the cells which are connected in series. So here cell series are connect module. So total EMF is equals to sum of the individual EMFs. So E1 and E2 and their internal resistance which are connected in series, right? So this is first case when both are connected, similar cells which are connected, right? So now if the cell interchanges the direction, right? So in the second case, so here we don't have any derivation, just replacing the cell. So here is positive, here is minus, changing the direction of any one cell. So minus plus. So if you observe these two, so here negative is connected to the positive terminal of the second cell. So here negative is connected to the negative of the second terminal, right? So E1 is the EMF and E2 is the EMF of the second cell. R1 is the internal resistance of the first cell and R2 is the internal resistance of the second cell. Then what about the E equivalent? So E equivalent is equals to E1 minus E2. Right? So direction change ಆಗಿರೋದ್ರಿಂದ E2 ಏನಾಗುತ್ತೆ minus E2 ಆಗುತ್ತೆ, right? So remaining as is R equivalent, that is equals to R1 plus R2, right? So if we change this one direction, so ಇದ್ರದ್ದು direction change ಮಾಡಿದ್ರೆ again ಏನಾಗುತ್ತೆ minus E1 plus E2. So ಎರಡರದ್ದು direction change ಮಾಡಿದ್ರೆ minus E1 minus E2, right? So this is when the two cells are connected in series, right? Next, so series simple agada, right? So now cells connected in parallel, right? So two similar cells, if we connected with the parallel means one end, that means both the ends of the cells are joined together, then we get the cells which are in parallel, right? We can take like this. So E1 is the EMF and R1 is the internal resistance of the first cell. E2 and R2 is the internal resistance of the second cell, right? So here A, so this point we taken as B1, B2 and C. So here the current flowing is I. So here also the current flowing is I. So at this junction the current divides I1, I2, right? So again, here it will combine I1 and I2 and we get the I, right? So now the potential difference across B1 and B2, across E1. So E cell ಅಲ್ಲಿ potential difference as similar procedure, right? So potential difference across B1, B2. So B1, B2 across cell E1. Across cell E1. So that is B1, B2. So we can write that as VB1 minus VB2, right? So we taken this one as common potential V, right? So that is equals to, again from the definition, E1 minus I1 R1, because I1 is the current which is flowing in the first cell, right? So similarly the potential difference across the cell E2, so we taken same potential VB1, VB2, so that one we can directly write V is equals to E2 minus I2 R2, right? So here these two cells V is equals to E1 minus I1 R1 and V is equals to E2 minus I2 R2, right? So now we relate this with equivalent EMF. So E equivalent and R equivalent. So this gives what? A C. Right? So the total current which is flowing across these two cells, we can write that one as I, that is equals to I1 plus I2. Right? So here from this relation we can find the I1, right? So I1 we can write this one as E1 minus V divided by R1. So this gives what? I1, right? So I1 is equals to E1 minus V divided by R1. So that is from this relation. So here also I2, that is equals to E2 minus V divided by R2. So here the flowing current is I, right? So substitute those two values in the total current I. So here we getting E1 minus V divided by R1 plus E2 minus V divided by R2, right? So again, by simplifying, E1 by R1 plus E2 by R2. So from these two terms we can take minus V as common. So from that we can write 1 by R1 plus 1 by R2, right? So the equivalent V, that is equals to E equivalent minus I R equivalent. So now the equivalent voltage is V, that is equals to E equivalent minus I R equivalent. So we need to relate it to the potential V, right? So by taking V to the LHS and if we simplify, so that is V into 1 by R1 plus 1 by R2, that is equals to E1 R2 taking LCM E2 R1 by R1 R2 minus I, right? So that means rearranging the terms here. So we need in the LHS the potential V, right? So that's why we taken interchanging the terms. So here also if we take the LCM, R2 plus R1 divided by R1 R2, right? So that is equals to V1 R2 plus E2 R1 divided by R1 R2 minus I, right? So lengthy simplification. It is this one V equivalent. So now this whole term, if we shift to the RHS, right? So V is equals to E1 R2 plus E2 R1 divided by R1 R2 whole divided, so minus I whole divided by R1 plus R2 divided by R1 R2, right? So here, if we take on the LCM and simplification, E1 R2 plus E2 R1 minus R1 R2. So this comes to the denominator R1 R2. So it goes to the numerator, that is from the reciprocal, that is R1 R2 divided by R1 plus R2, right? So R1, R2, R1, R2 get cancelled. So we get E1 R2 plus E2 R1 divided by R1 plus R2 minus R1 R2 divided by R1 plus R2, right? Now so this is what we, right? So from equivalent resistance, right? So equivalent EMF V, that is equals to E equivalent minus I R equivalent, right? So now comparing these two, right? So for comparing these two values, so in place of V, we can write E equivalent minus I R equivalent, that is equals to E1 R2 plus E2 R1 by R1 plus R2 minus R1 R2 divided by R1 plus R2. So in place of E equivalent, we can write E equivalent, that is equals to E1 R2 plus E2 R1 divided by R1 plus R2, right? So comparing these two. So in place of R equivalent, we have the term. So R equivalent, that is equals to R1 R2 divided by R1 plus R2. So this is what when we get the two cells which are connected in parallel, right? So this is what the final expressions when two cells which are connected in parallel, right? So when two cells which are connected in series, we can directly get E1 plus E2 and R1 plus R2. But here in parallel, we get E1 R2 and E2 R1, and that is the two resistors which are in parallel, one by R1 plus one by R2. We can write this one also like that, right? So if we take another reciprocal LCM and simplify, we get R1 R2 divided by R1 plus R2, right? So now if we take on these two ratios, right? So if we take on, so this will come under the special cases, right? So if we take on the ratio for E equivalent to that of the R equivalent, right? So in the numerator, we need to write the E equivalent, that is E1 R2 plus E2 R1 by R1 plus R2 whole divided by R1 R2 by R1 plus R2, right? So here in the denominator R1 plus R2 get cancelled, so we get E1 R2 plus E2 R1 whole divided by R1 R2, right? So further we can write E1 R2 divided by R1 R2 plus E2 R1 divided by R1 R2. So R2 get cancelled, R1 get cancelled, right? So we write this one as E1 by R1 plus E2 by R2. This is the ratio of E equivalent to that of the R equivalent, right? So if N So in our next class, we will discuss that is Kirchhoff rules. So in Kirchhoff rules, we have the two laws. One is Kirchhoff current law and Kirchhoff voltage law, right? So we will continue in our next class, right? Thank you.